This beautiful optical phenomenon is sometimes visible in the sky when the sun comes out after it's been raining. The arching colours of a rainbow are very distinctive. Yet you might be surprised to learn that the arched shape isn't just any old curve. In fact, all rainbows are sections of a circle. That circularity becomes more apparent if you piece some rainbow pictures together. The rainbow circle is one of several characteristic features that's explained by a mathematical model which has been over 2,000 years in the making. You'll see later on how the seeds of the modern theory were first sown by some theologians in the Middle Ages. They studied how rays of light behave within a homemade raindrop, in their case a flask of water. This was pioneering work, but it didn't compete successfully against the irresistible weight of religious explanations at the time. Ever since people first walked the earth, the appearance of a rainbow must have been marvelled at, and not too surprisingly, it's been attributed with mystical power. We can't know for sure what religious significance the Navajo artist gave to the rainbow, but it's thought that these symbols from the arid western deserts of Utah were important in encouraging rain. Elsewhere, it's known that the Iroquois and Hurons believed the rainbow was the wife of Hino the thunder spirit, one of the greatest of gods. Not unnaturally, perhaps, many other religions claim divine intervention in the rainbow's creation. If you're a Buddhist, you'll probably be very satisfied by the symbolism in this famous rainbow photograph taken over a Tibetan monastery. But there's a fundamental flaw with many of the explanations of religious origin, and that is that they firmly connect the rainbow with a single source of water, such as the falling rain. Yet the phenomenon can also happen in other settings where water droplets occur. Here's a waterfall bow at Niagara. It certainly looks like a rainbow. How is it caused? The Native American tribes put forward a reason to account for this coloured arc, which is sometimes visible in their waterfall.
Yeah, we used to come here and sacrifice things, or give things to the falls to honor it. We used to take a young Indian girl, very young woman, put her in a canoe full of goods, like plants to eat with, and things, offerings to eat. Used to send them down the river, go over the falls. And you would see them people later when the rainbow comes out over the falls. That rainbow is the bodies of these women. It's beautiful.
The legend of these maids of the mist is preserved in the name of the pleasure boats that brave the spray at the foot of the falls. Clearly, it's not just the sun and rainfall that can lead to a rainbow. Spray or mist seem to be just as good, as in this case, in the spray from an oil platform hose. Or even from the hoses of the fire brigade. But whatever the name, the phenomenon seems to involve sunlight shining on water droplets. But you don't automatically see a rainbow when the sun illuminates spray. It seems that you have to view the water droplets from a particular position. There's a number of features which you can see are common to all bows if you spend a little time studying them. For example, you might think about why the rainbow can adopt various positions in the sky. At some times of the day, a bow might arch high into the sky, and at other times it might appear lower down on the horizon. And as you've seen, there's the circularity of rainbows. And then there's the colours. Sometimes they're pastel shades. and sometimes vivid colours. Yet they always appear in the same order, ranging from red to violet. You might have seen that this same set of colours can be produced when a glass prism is held up to the light. The way that the prism refracts or bends rays of light into this spectrum of colours might well have a part to play in the formation of the rainbow. But it turns out that the simple refraction of light, like this, can't be the only mechanism involved. Because, in addition to the colours, the various positions in the sky, and the circular shape, there are other features to be accounted for. Have a look at this painting of a famous rainbow. It shows more than just a single bow. There's another arc further out above the first. This is not just an invention of Rubens the artist. Although he has lit the characters from the side, which you'll see means that Rubens took artistic license with the position of his double rainbow. The lower bow of a double rainbow is called the primary, and the upper bow is called the secondary. And if you look closely at the fainter colours of the outer secondary bow, you can see that the order of colours is reversed, with red now below the violet. In fact, another feature of rainbows that's often overlooked is the existence of a darker area of sky above the primary, which stretches all the way out to the secondary. This is known as Alexander's dark band, after Alexander of Aphrodisias, who originally drew attention to it in about 200 AD. So, altogether, including the double rainbow and Alexander's dark band, there are at least 5 features to be accounted for. Assuming that you're not entirely satisfied with explanations based on divine intervention or sacrificial rites, then you might be interested in looking at some mathematical models and the history of how they developed into today's explanation. The mathematical approach is to develop a model and then refine it to fit the data. Over the years, there have been many theories, but all have been lacking in some aspects. One stumbling block which lasted for centuries was a controversy over whether the rainbow involves an entire cloud or individual raindrops. The Greek philosopher Aristotle, in about 300 BC, constructed an explanatory model which assumed that the entire heavens were a sphere. At the centre of the Greeks' universe was the earth, and so at dawn, say, the sun is on the horizon at the edge of the universe. Aristotle argued that the rainbow effect was then caused by the reflection of sunlight on a cloud, at a point where the distances from the sun and from the earthbound observer were in exactly the right fixed ratio. An easier way to think of this is that the angle between the rays will be fixed. Aristotle said that the rainbow had a circular shape because the universe was spherical. So the same effect would be created in all directions. Rotating the diagram about the line from the sun to the earthbound observer gives 2 cones of light, one spreading out from the sun, surrounding an inner one converging on the observer's eye. You'll be seeing that this part of the model isn't very different to our present-day explanation of a bow's circularity. But Aristotle's view fell down in other respects, and particularly when it came to explaining the colours. He said that red light was stronger than, say, blue, because red travelled a shorter distance from the sun to the cloud. That made the critical ratio slightly smaller for blue, and that's why the red cone of light surrounds the blue cone, and hence the red arc is seen outside the blue arc. Alexander disagreed with Aristotle's theory, since it didn't explain his dark band, and it didn't account for a reversal of colours in the secondary bow. However, Aristotle's model did account for the constant angle drawn from the top of the bow down to the top of the observer's shadow. You can see that a circular bow is a consequence of rotating this fixed angle made with the shadow line. From the ground, you see at most half a circle, but you can see more than half a circle if you go up high enough and have a ready supply of water droplets close by. Then, much more of the rainbow circle can be seen in the water droplets. Aristotle didn't measure the fixed angle from the shadow out to the bow. In fact, that was left to a 13th century Englishman, Roger Bacon. He measured the angle to be 42 degrees. But knowing the angle of elevation didn't solve all the problems. For 400 years, Islamic and Christian scientists were still to argue about the physics. Is the light just reflected back from the cloud, or is it somehow bent or refracted as well? Is the whole cloud involved in creating the bow, or can the behavior of light in individual raindrops be used to explain the effect? At the start of the 14th century, Kamal al-Din in Persia and a German monk, Theodoric of Freiburg, each independently concluded that both reflection and refraction have a part to play, not only in the cloud, but also in each spherical raindrop. Theodoric placed flasks in the sunlight and filled them with water to model how light rays might behave in a raindrop. He then drew construction lines, showing how the rays were reflected off the back of the flask and were also refracted into and out of his raindrop. He believed that each drop in the cloud created a part of the complete rainbow. Theodoric was actually very close to fully describing light's behavior within a raindrop. A ray of light striking the drop at its center will mostly pass straight through. However, some light will be reflected straight back from the back of the drop. But another ray hitting the drop away from the center line will be refracted as it enters. Then some of the light will reflect off the back of the drop, at an angle, to be refracted again as it leaves. At other entry points, the light exits in other directions. But what's important to the rainbow's creation is that no light exits at an angle greater than Bacon's 42 degrees to the sunlight. And also that there is a high concentration of light near to that fixed angle. You can see how much of the light that enters on one side of the center line exits at this 42-degree angle on the other. But the drop isn't a circle, it's a sphere. And so this light enters at points all around the center line and exits as a cone of light, which is clearer to visualize if the incoming light is hidden. The concept of a cone dates back to the 14th century, but an explanation of the colors had to wait 300 years. Then, mathematicians such as Newton observed that sunlight is a mixture of many colors, and each refracts differently. Consequently, red light returns a cone of light looking like this, whereas the cone for violet light looks like this. That's what happens in a single raindrop. But what about all the other raindrops in the cloud? These can be thought of as filling all parts of the cloud, because even though they are constantly falling, they are being continually replaced. Sunlight, hitting drops in the cloud, will return as cones of coloured light. High up in the cloud, the coloured light is cast above the observer's head. Lower down, the returning light gets nearer and nearer to the observer's eye, until there comes a point at which first part of the red cone reaches the observer's eye, but not the violet cone. However, from a drop a little lower, just the violet light reaches the observer. The angle from the observer's shadow up to the direction of coloured light is about 42 degrees, as Bacon had measured. But remember, this is just a sideways view. And this is not the only place in the cloud that returns light at 42 degrees to the observer's shadow line. For instance, there will be another drop to the side, which is still at 42 degrees to the observer's shadow. And another one here, again at 42 degrees to the shadow line. And so on, from certain drops all around the cloud. It turns out that the parts of the cloud from which this rainbow light can be seen lie within the arc of a circle centred on the line of the observer's shadow. So, you have an explanation for the rainbow's shape and its colouring. But what about the differing positions in the sky? The basic 14th century model can also explain that. It depends on the length of the shadow. As the sun rises higher and higher into the sky, your shadow shortens, and since there are no raindrops below your feet, less and less of the rainbow is visible from the ground. With the help of the fire service, we were able to take the camera high into the sky and get sufficient droplets below us to see nearly all of the full circle of the rainbow. Filming from the ground just rewarded us with the top of the circle. Now what about the secondary bow? How does the light for that come about? Well, not all the light leaves a raindrop after a single reflection. A little light is reflected a second time before escaping. And just like in the primary bow, there's a fixed exit angle for much of the light that's been reflected twice. This other exit angle is at about 51 degrees to the sunlight. These were the primary cones. The secondary cones are spread more widely. But because of the two reflections, the colours are reversed, forming not a red but a violet outermost cone. In the rain cloud, the colours of the primary bow came from drops fairly low down in the cloud. For the secondary bow, raindrops near the bottom of the cloud return these additional cones of light, which aren't visible to the observer. But progressively higher in the cloud, the returning light gets closer and closer to the observer's eye, until eventually raindrops are reached where first just red light, and then higher still in the cloud, just violet light can be seen. The angles of elevation to the red light are then 42 degrees to the top of the primary and 51 degrees to the bottom of the secondary. Surrounding drops return light which is visible as this second circle outside the primary. That's a mathematical account of most of the features, except, that is, for a proper explanation of the dark band. Remember, that's the darker area of sky between the primary and the secondary bows. In the 17th century, both Descartes and Newton explained this. They clearly established that light only comes out of the cloud below the primary bow or above the secondary bow. And so the sky in between them doesn't get any extra illumination. Interestingly, Newton is also responsible for specifying the colours. He thought that there ought to be as many colours as the 7 notes in a musical scale, and had to fiddle his results to prove it. So, is the rainbow fully accounted for? Well, the answer is no. There are other features awaiting explanation. For instance, if you look carefully at the underside of the primary bow, you can sometimes make out some red and green bands below the violet. These are called supernumerary bands. The mathematics of Newton couldn't explain their existence, but modern ideas, including the wave-like properties of light, do provide an explanation. Nowadays, physicists can also study the rainbow effect given droplets of different sizes and even of different shapes. Indeed, the droplets don't even have to be made of water to get the effect. Here's a demonstration at a public lecture on the rainbow, in which a circular bow is created by shining a light on tiny glass beads stuck to a dark screen.
What we're using to create the rainbows is this fibre optic illuminator. We have a fibre bundle here, which at the other end there's a very intense halogen.
The circular bow is certainly convincing, but what's been a mystery are some coloured bands created very close to the source of light.
These rings are a diffraction phenomena, and what we're seeing is light reflecting from the backing and then being diffracted as it passes through the glass beads. So, to some extent, the jury's still out on that one.
Some questions require more maths and physics, but many questions can be answered with the basic theory. For instance, if one person can see a bow in the sky, what will a companion, sitting alongside, expect to see? The answer is their own rainbow, because each bow is formed about an individual's shadow. In this picture, it looks as if the image in the water is a reflection of that rainbow in the sky. But is it? If you think about it, that must be a reflection of another bow, one which you can't see. Let's end the programme with this rare phenomenon, captured on film in the Highlands of Scotland. How is it possible that there's more than one primary and one secondary? And how can two bows intersect? Think about it a moment. Imagine yourself on the opposite bank, looking back across the water. From there, you might well see one sun in the sky and a second sun, its reflection in the water. And both these suns produce rainbows.